Welcome to Understanding Data Transmission Modules. My name is Lukas Tanutama. I'm a lecturer of the Computer Engineering Department of Binus University. The topic of this video series is Understanding Data Transmission. I will present the important concepts of data transmission that enables today's communication activities. Data transmission is not flashy, but without data transmission, no electronic communication is possible. Data transmission is the backbone that enables us to communicate effectively and perform all kinds of activities. It includes also human to machine, machine to machine, and machine to human communication. I hope that understanding the concepts can help in enhancing your knowledge. The presentation is more on the practical view and qualitative description. Enjoy the modules. Thank you. Essentials of Data Transmission, Module 1, Fundamental Theory. Signal. In communication systems, mathematical tools are used to describe signals and noise. Communication signals are represented in electrical waveforms. The properties of these waveforms are DC value, power spectral density, and bandwidth. Digital communication signal waveform is commonly represented by a square wave. Fourier theory. Basic concepts. Fourier shows that a square wave is made up of a sine wave at the fundamental frequency of the square wave plus an infinite number of odd harmonics. Fourier allows us to determine sine wave components in a complex signal. These sine wave components are the complex signal frequency spectrum that determine the signal's bandwidth. In this slide, you will see a sine wave and its harmonics that are part of a square wave. Time domain versus frequency domain. Analysis of variations of voltage, current, or power with respect to time are expressed in the time domain. A frequency domain plots amplitude variation with respect to frequency. Fourier theory gives a new and different way to express and illustrate complex signals with respect to frequency. Fourier transform. The Fourier transform provides the mathematical tool for measuring the frequency content or spectrum of a signal. For this reason, the terms Fourier transform and spectrum are often used interchangeably. Time and frequency relationship. If the time domain description of a signal is changed, the frequency domain description of the signal is changed in an inverse manner and vice versa. If a signal is strictly limited in frequency, the time description of the signal will trail indefinitely even though its amplitude may assume a progressively smaller value. Bandwidth. Bandwidth is a measure of significant frequency or spectral content of the signal. When the signal band or frequency is limited, the bandwidth is well defined. There are some commonly used definitions for bandwidth, such as the commonly 3 dB down bandwidth. Three dB bandwidth, low pass type. The separation between zero frequency and the positive frequency at which the amplitude drops to 1 over square root 2 of its peak value. Bandpass type. The separation between two frequencies at which the amplitude spectrum of the signal drops to 1 over square root 2 of the peak value at frequency C. Fourier transform and non-sinusoidal wave. It is often needed to know the frequencies that are present in a waveform, specifically waveforms that are of non-sinusoidal type. Non-sinusoidal waves have more than one frequency. In most practical application, the waveform is not periodic. A general method for finding the frequencies of a waveform that will work for any type of wave shape is the Fourier transform. It finds the sinusoidal type components in that non-sinusoidal wave. Power. In communication systems, if the received or average signal power is sufficiently large compared to the average noise power, information may be recovered according to Shannon channel capacity formula. The instantaneous power, incremental work divided by incremental time, associated with the circuit is given by P of t equal to V of t multiplied by I of t, where the instantaneous power flows into the circuit when P of t is positive and flows out of the circuit when P of t is negative. Power spectral density. To know the frequency domain distribution of power, the Fourier transform of the signal is needed. The total area under the curve of the power spectral density is equal to the average power of that signal. Power signals have infinite energy and may not be Fourier transformable. To overcome the problem, a truncated version of the signal is used. Power spectral density. The normalized power of a waveform will now be related to its frequency domain description by the use of a function called power spectral density. The PSD is very useful in describing how the power content of signals and noise is affected by devices in communication systems. The PSD is useful models for solving communication problems.